Hey, all you Greta's and Shutez cats out there. Welcome to Unit 1, Section 5, Thermodynamics and Energy Flow. So, let's get started. Energy. So this is in your notes under Section 5 where it says energy flow and primary productivity. So energy flow, or energy, is the capacity to do work or to transfer heat. Kinetic energy is moving energy, usually with mass and velocity. So things like wind, heat, electricity, flowing water, and then potential energy is your stored energy. So if something is moving, it's kinetic, and if it is not moving, it is stored. Cats are great at moving something from its potential energy to its kinetic energy when they knock it off the table. So you're using energy, you're not at the top, you just have a lot of potential, and then energy out down at the bottom. All right, first law of thermodynamics. We will be doing an activity this week dealing with the first and second laws of thermodynamics. It will be fun, I promise. So the first law of thermodynamics, energy cannot be created or destroyed, but it can be changed from one form to another. When you eat food, you take the chemical energy in the food and it's used through your mitochondria to be turned into the ATP that your body can then use as an energy form. And then part of it is given off as heat as well, but it's changing from one form to another. So that's the first law. Ice cream, chemical energy into the kinetic energy of kids bouncing off the walls, light energy from the sun into the chemical energy in. Always equals, can never be created or destroyed. It's just changing forms. Second law, the increase of entropy. So what this means is energy quality is always going to decrease. So as you go from one form to the next, it is a lower quality form of energy. So you don't lose energy, it just becomes a lower quality form. When energy changes, it is always degraded to a more dispersed form. So energy efficiency would be how much useful work is accomplished before it changes. How much stuff can you get from that energy before it's moving on to that next form? So you can think of this with food. You have high, good, energy dense food. A peanut butter and jelly sandwich on whole wheat bread is going to give you a lot of energy and calories to get you going through the rest of your day versus like a bag of chips. So something to think about. We have our sources of energy over here from very high to very low, and then our energy tasks from high to low. The best way to be energy efficient is to match the heat or the energy task requirement with something that with the same level source of energy. So for low temperature heat, for space heating, we don't need stuff up here. You can just use geothermal heat, and we can have this here in Indiana. You can get your houses retrofitted for this. It's a little pricey, but then once it's set up, you use the heat of the earth to heat your home. That's pretty cool. Versus high temperature heat things, industrial processes, and electricity to run more of your electronic devices, lights, motors. So we have our fossil fuel electricity, but we also have solar and wind is up here. So we can totally have our high sources of energy that are not being produced using fossil fuels. We have other options. So how do humans fit into all of these shenanigans? So our enjoyment of life is a reduction of local entropy. We are focusing on what we are doing and what we needing, but it comes directly at the expense of polluting the environment. So you turning on the light or you heating your home is great for you and your entropy is less, but it results in the polluting of the environment and the increase of total global entropy. So there is no such thing as a free lunch. You're paying for it in some way. Law of conservation of mass. So for any closed system, which is the Earth, unless aliens start sending us care packages, we're a closed system, the mass has to remain constant over time. So we're not consuming resources, we're just borrowing them and transforming them. So if I had a Lego spaceship and I broke apart all of the Legos and made it into like 4 or 5 smaller things, I don't gain any Legos and I don't lose any Legos. They're just in different forms. So the same with conservation of mass. All of the atoms we have are all here and they're not going anywhere. They're just changing. So when you set something on fire, it's giving off a lot of all that carbon in the wood is going to go up into the air in the form of CO2. All the minerals are going to be left in the ash. So everything is still there. It's just different. But every atom is accounted for. Law of conservation of mass. So what is the relevance to our class? Environmental science, pollution. Most actions out there that make our lives easier are going to cause pollution in some way or another. So we will always be faced with pollution of some sort. We need to figure out what kind. Can you tell it's Friday? We need to figure out what kind, and then what can we do to reduce it. So think of this. This is crazy. So if we have 300 trout, which is a fish, are needed to support one man or woman for a year, the trout in turn must consume 90,000 frogs. That must consume 27 million grasshoppers, and that live off 1,000 tons of grass. So for one man, we need 1,000 tons of grass. That's a lot of grass. So what is this referencing? You can think food pyramid, you can think food chain, and that's what we're going to talk about next. So on your paper, you've got some matching vocabulary. These are not going to be in order, so pay attention. You may have to pause and write stuff down. So your predator is going to kill and eat something. It eats things that it kills. There we go. Like the lion or poor little guy, or this cat or the shark. An omnivore is going to eat plants and animals. So you have options. Most of you are omnivores. A consumer heterotroph, it needs to eat to survive. Look at the little pigs. They're so cute. But you need to eat something to survive. So consumer consumes. Heterotroph literally means different and food. So you need a food that is different from you. You're having to take it in from something else, a different source. Decomposers are going to break down organic matter into inorganic matter. And the two only true examples of decomposers are your bacteria and your fungi. And we need these guys because if not, we'd be up to our eyeballs in dead stuff and poop. And I don't know about you, but I don't want to be up to my eyeballs in dead stuff and poop. So we need these guys to break all that stuff down. Producers and autotrophs, these are going to be mainly your plants or your blue-green algae, which is a falsely named thing for cyanobacteria. So we have sea plants, we have land plants. 99% of these guys use photosynthesis. A very small percentage, like 1%, does chemosynthesis using the sulfur vents in the bottom of the ocean to make their own food from the sulfur. Pretty hardcore. Primary consumers are the first level of things to eat. Primary consumer. So I am a primary consumer. These things are going to eat plants or producers or autotrophs. We've got options. The detritivores, so these are going to start breaking stuff down for the decomposers. So these are a lot of your creepy crawlies, and they're going to break down the leaves and nature's trash and break those all down into smaller pieces for the decomposers to take care of. So worms and slugs and pill bugs and all those fun guys, or isopods is the fancy word. Carnivore eats meat. That is a terrifying tarantula. But carnivores eat meat, so they have to be at least secondary consumers because they will eat the primary consumers. Secondary consumers are that second level that eat stuff. So secondary consumers can be omnivores or carnivores. It depends on the critter, but it is the second level that eats things. So keep in mind you can have overlapping terms. Things like a sea turtle is a secondary consumer, a heterotroph, and a predator. Gorilla is an omnivore, a predator, and a heterotroph. And the pill bug is a detritivore, a consumer, and an omnivore. So the other question on that page is what trophic level supports all the other levels? If you got rid of one, which one would affect everything else in those terms? I would go to the bottom of the food chain and look at your producers. All righty, next page. So the next page kind of flips around and it says draw a food chain, and that's going to go off an article that's a little bit later in your packet. So I'm going to skip that for now. Do this, just don't do it this second. Or pause and do it and then come back. But we're going to go on to ecological pyramids, which is the next thing. So these are graphical models of the differences between trophic levels of a single ecosystem. So you can have three kinds. You can have an energy pyramid or a trophic pyramid. Remember, trophic means food, and you get energy from food. Biomass pyramid or pyramid of numbers, which is literally how many of each critter you've got. Pyramids usually become narrower towards the top, hence they're called pyramids. So you can have pyramids of energy. You have your producers at the bottom, then your herbivores, then your carnivores, then your top carnivores. A lot down here, less as you go up. There's the 10% rule. So they're going to show the flow of energy through the trophic level. Energy goes from the sun to the plants, to the things that eat the plants, to the things that eat the things that eat the plants, to the things that eat the things that eat the things that eat the plants. 90% of the energy is lost at each transfer, and that's where that 10%. So only 10% of the energy is passed on. Okay, energy is not lost. We already talked about that. It becomes a lower quality form. So the conversion efficiency is the ratio of net production of one level to the next. So we have about a 10% efficiency getting passed on. Not very efficient. Pyramids of energy, can they be lost? So the lost energy, it's lost as feces, as urine, and then used in respiration and lost as heat. So cellular respiration is how you make your energy to keep you going, and then to keep you alive, keep you warm. So a lot of that is lost there. So if you have 1,000 kilocalories of producers, you'll have about 1,000, Friday. You'll have 100 kilocalories in a primary consumer. Only 10 of those calories goes on to secondary, and only 1 goes up to tertiary. So that is why we have way, way more producers than we're going to have of your owls or tertiary consumer. Then you can have pyramids of biomass, so biomass is the total mass of all the organisms in the area. The missing mass, the ones that are not eaten, will become detritus and decompose, like your compost bins. That's a good way to use your biomass productively. Here is an example. So grass, snowshoe hare, red fox, and wolf. You can see, I'm not reading all these numbers for you, but you can see how the numbers go down as you go up. It's measured in weight per area, so grams of biomass per square meter. You can have a pyramid of numbers, which is literally how many of each thing. This many producers are eaten by this many consumers, secondary, tertiary. Number of individuals at each trophic level. Now, you can have different kinds of pyramids of numbers depending on the ecosystem. So your typical pyramid is like the ones I've shown you guys. This guy here shows the effect of a large producer such as a tree. So if you're looking at a single tree or even a forest that's still limited versus like a grassland with lots of little blades of grass, which are each counting as one thing. So you have one tree being eaten by a lot of caterpillars and then being eaten by the birds. And then this one over here, if it's upside down, this is your typical parasite. One rose bush is eaten by a lot of aphids, and those aphids are eaten by a lot of parasites. So more often than not, if you see an upside down pyramid, you're dealing with some type of a parasite. So talking about inverted pyramids, it's either you have trees, is the main example, or a parasite. So one English channel, the producers in there going up. Click. So inverted can happen in pyramids of numbers and biomass, and usually occurs in the numbers category because of what I said earlier with parasites. Now, it can also result with seasonal fluctuations, weather, and natural disasters, but like I said, more often than not, it's a parasitic situation. Now, can an energy pyramid ever be inverted? No, it cannot. So it doesn't work that way. You can't start with a little bit of energy and then increase as you go up. It's like the opposite of the second law of thermodynamics. So how are they relevant? So as the energy is transferred along, it's changing form, but as it's changing form, it's becoming a less high quality form. And you will see this hopefully better once we do our activity in class. Virtual students, stay tuned I will send you the data. Now, if you go back, there is that group activity. So there is in your packet, and you can find the link on the online version, this article. It all started with a few trout. So you read this and then you'll build a food web based off of this activity. And they give you a lot of the critters on the page So it should be fairly easy for you to get that set up. And you have survived this round of notes. So before I go, I want to remind each and every one of you that you are good enough, you are smart enough, and people like you. And if I don't see you, good afternoon, good evening, and good God, do your homework.